Evaluate the double integral of the function sine of x squared plus y squared over the region R with respect to the area, where R is the region in the first quadrant between the circles at the origin with radii 1 and 5. Okay, well, that's a lot, and it's a lot of words, so let's turn words into a picture that we can understand. So let's go ahead and graph what R is. What are they talking about when they say R? Okay, so I have my xy plane. Okay, circles. So there's two circles that are both centered at the origin, and they have radii of 1 and 5. So let's draw our smaller circle. It has a radius of 1, which means that it's intersecting at 1. And then 2, 3, 4, 5, right? We have a bigger circle that comes out, all the way to here. The circle is probably going to look terrible, but yeah. Okay. Whatever, you get it. And then region of this that is in the first quadrant between the circles. So first quadrant is this quadrant, right? This is quadrant 1. So first quadrant between the two circles. So let's go ahead and color that area in, shall we? All right. Like I'm being so careful about coloring my crappy circle. All right. So this is R. And great. So, oh, okay, yeah, and this intersects at 5. So don't forget that. All right, the double integral of that. Now, this is not very intuitive to do in Cartesian coordinates, right? So we're going to go ahead and switch over to polar coordinates because a shape like this is very intuitive and easy to represent in polar coordinates, right? So let's go ahead and define our bounds in polar coordinates. Polar coordinates I go over in a different video how they work, so if you want to figure that out, then look that up and you'll find it. But the bounds are, let's look at our bounds for our radius. So radius going from the center, it starts at 1 and it goes all the way out to 5, right? So R is greater than or equal to 1 and is less than or equal to 5. Then our angle, theta, right, going from the positive x-axis over this way, goes from 0 to pi over 2, right? Okay, and that was theta right here. And then this distance right here, right, is r. Now we have our bounds that describe the shape. Now let's rewrite our double integral to make sense of this. So when we're rewriting in polar coordinates, when we're rewriting a double integral in polar coordinates, one thing that we want to keep in mind is that our identities. So x is equal to r cosine theta, and y is equal to r sine theta, right? And one other identity that's useful to know, right, which you could work out from these two, but we don't want to do that. That takes too long. So x squared plus y squared, which is something you'll see all over the place, is equal to r squared. Okay, now that we have all of these, we can go ahead and substitute it into our equation and work out from there. But one other thing that we want to keep in mind before we do that is that whenever we're applying this to a double integral, dA ends up being equal to r dr d theta. Okay. Always going to be this. So given all that, let's rewrite what we had up there. So we have double integral of sine of, well, this is x squared plus y squared, and we have an identity for that, so that's r squared, sine of r squared, r times r, right, dr d theta. Great. Okay, now that I have all of that, we need the bounds so that we can do our integration. So our first bounds that we're going to have right here on the inside is going to be our bounds for r, right? So r goes from what? Goes from 0 to 5. And theta goes from 0 to pi over 2. Okay, now that we have this, let's go ahead and get it by itself, and we'll work through it. Okay, so let's start with the inside integral first. So the inside integral is this part right here with respect to r, right? All this. Okay, so integrating sine of r squared with respect to r times r, well, we can use u substitution. So u equals r squared, du equals 2r dr. Okay, then if we plug that back into here, then we rewrite our integral with u in mind. So we plug our lower and upper bounds into our equation for u, right? We plug them in as r. So 0 squared is 0. 5 squared is 25, right? And then we have sine of u times r, right? And dr is equal to what? Well, let's solve for dr down here. This equation turns into dr equals du over 2r. Okay, so let's replace that in here, times du over 2r. Great. Now our r's cancel out, which is great because we don't want any r's left over when we do u substitution. We don't want to have any of the original variable left over. We only want to be left with u and du. So this is good. Great. And this all simplifies to 0.25 sine of u over 2 du. And that should be pretty easy to solve. Okay, so the integral of sine of u is just negative cosine of u, right? And since the 2 on the bottom is just a constant, all that stays the same. So we end up, this is equal to negative 1/2 cosine of u going from 0 to 25, which then equals, plug in our upper bounds, so minus 1/2 times cosine of 0 times, or not times, minus, plug in our lower bound, is going to be minus 1/2 times cosine of 0. And let's, oh wait, no, sorry, upper bounds, not lower bounds for this right here. So this is 25, not 0. My bad. All right, so let's plug it in, shall we? So what we end up getting from that. Okay, I was just looking at it. I don't think that 25, the cosine of 25, even in radians, can be reduced to anything other than just a decimal number. So what we're going to end up here is just negative 1/2 times cosine of 25 minus cosine of 0 is just 1. Okay, so now we're going to take this part that we have down here, we're going to plug it back into our second integral right here. So pi over 2, 0, get negative 1/2 cosine 25 minus 1 d theta, which is just going to be equal to, since this whole thing right here just comes out to being some constant, then we just tack a theta onto the end of it, and that's that. So minus 1/2 cosine 25 minus 1 theta from pi over 2 to 0. Okay, then if we ended up plugging in pi over 2, then we get 1/2 cosine 25 minus 1, and then that would be minus whatever it would be when we plug in 0, but since if we plug in 0 for theta, that multiplies to the whole thing, and that just ends up being 0. So it's minus nothing. It's just this value right here. Or actually, sorry, I didn't even multiply that value by pi over 2. So we have pi over 2. Great. Now if we take all that and we simplify it, then we have pi over 4 times cosine of 25 minus 1. And that is your answer. All right, a couple of mistakes that I made here, actually, so that's not the answer. The first one is all the way up at the top here. I went from 0 to 5 for r, when that wasn't our bounds. We look back here, our bounds go from 1 to 5, not 0 to 5 for r. So let's fix that. 1 to 5. Okay, now when we plugged our 1 into our function for u to get our lower bound for our new with u substitution, we plugged 0 into r squared and got out 0, but it should be 1, not 0. So this changes to a 1, not a 0. Which means that when we plugged in 1 for our lower bound here, this should be a 1, not a 0. Cosine 1. Great, which means that this does not simplify to 1, it's still cosine 1, which is just some number. We don't know what it is, right? Now let's rewrite the rest of this with all that in mind, because this is cosine 1, sorry, this is cosine 1, this is cosine 1, and this is cosine 1. Okay, there's that fixed. The last mistake that I made is I left out the negative on this 1/2 right here. Okay, now after all of that, after fixing all of that, we can simplify and we get negative pi over 4 times cosine 25 minus cosine 1. And that, I am 100% sure, is the correct answer. Alright, just to go over everything that we did from the beginning. So, we were given a function and a description of what the range of what the range that that function is to be integrated over with respect to the area. So R was given to us as the region in the first quadrant between the circles at the origin with radii 1 and 5. So we went ahead and drew that out. We had two circles with radii 1 and 5, and we picked the area that's between them that's also in the first quadrant. We translated that into bounds, but because this is more intuitive to do in Cartesian coordinates than it is sorry, not more intuitive in Cartesian coordinates, more intuitive to do in radial coordinates than it is to do in Cartesian coordinates. We converted it to radial, and that is a radius and an angle theta, right? We defined it as being between 1 and 5 for the radius, and 0 to pi over 2 for our theta. We noted that our proper substitution for conversion to polar coordinates, sorry, not radial coordinates, polar coordinates. Our conversion polar coordinates here, that x is equal to r cosine theta, y is equal to r sine theta, and x squared plus y squared is equal to r squared. And dA turns into r dr d theta. We used all that. We used all that to rewrite our integral. We used our limits for r, 1 to 5, and our limits for theta, 0 to pi over 2. We rewrote the inside as sine of r squared times r dr d theta, as we said. And then we integrated the inside part using u substitution. We rewrote our bounds using our equation for u. And then we substituted in. We ended up with something that just had u and du, so we were good to go. Integrated and then substituted in our bounds. Then we did the second integration on the outside. We integrated, plugged in, we integrated for theta, but since relative to theta, this whole thing's just a constant, right? How we integrate with that is we just slap in a theta onto the end, and then we do that for the range from 0 to pi over 2, and that came out to this number, right, or this right here, which simplified to our end answer. All right, well, if this helped you out any, sorry for all the mistakes that I made along the way, but if this helped you out any, leave a like, leave a comment, and let me know what you think I should go over next. I have plenty other, or a few other examples that I walk through of doing integration and other things that you can find in Calculus 3. So if you're interested in any of that, consider looking around my channel. Have a good day.